Hello, learners. I'm Dr. N.Sudha, working as an associate professor in PG and Research Department of Physics, Sri Sharda College for Women, Salem. Today, we're going to see an interesting topic that is surface tension. Physics is a fascinating subject that explores the fundamental principles underlying the behavior of universe. It seeks to understand the nature of matter, energy, space, and time. From tiniest subatomic particles to the vast expanse of cosmos, physics helps us to uncover the mysteries of how the world around us works. Physics not only uncovers the fundamental laws of nature, but also drives technological innovation and inspires deeper philosophical questions about nature of reality. Ever wondered why raindrops are spherical in shape or any droplets of water formed on the leaves assume spherical shape? Let's see the reason for this. Any liquid in small quantity that gravity influence is negligibly small will always assume the form of a spherical drop. Example, raindrops, small quantities of mercury placed on a clean glass plate. So, a liquid must experience some kind of force so as to occupy a minimum surface area. This contracting tendency of a liquid is known as surface tension of the liquid. This is a fundamental property of every liquid. Surface tension is the reason for this. So, surface tension is the tendency of the liquid surface to shrink into the minimum surface area possible. A liquid must occupy some kind of force to attain this minimum surface area. So, this contracting force is called as surface tension. You can very well see here in this diagram, there is liquid, these are liquid molecules, and it is being pulled by all the sides so as to assume the minimum surface area possible. So, this happens for all the molecules within the liquid. To understand surface tension even more deep, we should know the two kinds of molecular forces. They are adhesive force and cohesive force. Force of attraction between the molecules of different substances is called as adhesive force. For example, the force of attraction between glass molecules of a beaker and molecules of water contained in it is an adhesive force. Adhesive force is different for different pairs of substances. Force of attraction between molecules of same substances is known as cohesive force. This force varies inversely, probably as the eighth power of the distance between the two molecules. Hence, it is very appreciable when the distance between the two molecules is small. It is greatest in solids, less in liquids, and least in gases. Therefore, a solid has definite shape, a liquid has free surface, and a gas has neither. This picture very clearly shows that the force of attraction between oxygen and oxygen molecule or water molecule together is cohesive force. Whereas the force of attraction between water molecule and this material, or maybe you can take it as steel or the container, is called as the adhesive force. Surface tension is responsible for several interesting phenomena that we see in day-to-day life. One best example is the capillary action. So, capillary action. This is the ability of a liquid to flow against gravity in narrow space, such as thin tube or straw. Surface tension pulls the liquid up the sides of the tube due to the balance between the adhesive force between the liquid and the tube walls and the cohesive force within the liquid. Next example is very interesting. It is the droplet formation. Surface tension causes the liquids to form spherical droplets, as this shape minimizes the surface area for the given volume of liquid. Raindrops, water beads on the surface, and liquid drops of various shapes are best examples for this phenomena. Insects walking on water. Most of us have seen insects walking on water, and we would have wondered how it is able to balance on it. It is because of surface tension. Insects like water striders are able to walk on surface of water due to the high surface tension of water molecules. The cohesive forces at the water surface support the weight of the insect, so it is able to walk on the water surface. Soap bubbles. Surface tension is responsible for the formation of soap bubbles. The film of the soap solution between the layers of bubble reduces the surface tension, allowing the bubble to expand and maintain its shape. Meniscus formation. Most of us would have seen the lower meniscus or upper meniscus in our laboratories. So it is a curved surface between any liquid and the glass. So when you look at a curved surface of water in a glass, you are seeing the result of surface tension. The liquid is pulled either up or down the edges due to the adhesive forces between the liquids and the container. Almost certainly, you have used a brush paint at least once, if not many times in your life. So it is not exactly the wetness of the brush that makes the hand cling together, rather it is a phenomenon of surface tension. Now, let us see the definition of surface tension and the units of surface tension. Surface tension is defined as force per unit length of line drawn in a liquid surface acting perpendicular to it at every point and tending to pull the surface apart along the line. Now, how to find the unit of surface tension? We know surface tension is actually force by length. Unit of force is Newton and the unit of length is meter. So, it is Nm power minus 1. The unit of surface tension is Nm power minus 1. Dimension of surface tension. We know the formula for surface tension is written as force by length, or it could be rewritten as force into length per minus 1. The units of force is mass into acceleration, and the acceleration is actually velocity by time, or velocity into time per minus 1. Velocity is again written as distance by time, or you can again write it as distance into time per minus 1. So acceleration actually becomes L t power minus 2. Okay. And so the dimensional formula for force is actually m power 1 L power 1 t per minus 2. Now substituting this in equation 1, we get force into L per minus 1. So force is m per 1 L per 1 t per minus 2, and length is written as L per minus 1. So it becomes m per 1 and t per minus 2. So therefore, surface tension can dimensionally represented as m per 1 t per minus 2. The effect of gravity and surface tension on the formation of drops. So gravity influence is very important in the formation of drops or the spherical formation in drops. So if it is a small drop, surface tension is great and the effect of gravity is small. So rainwaters are always spherical in shape. If the water droplets are big, then surface tension is small and gravity effect is big. So the drops become flat in nature. Let me now explain surface tension based on molecular theory. Consider three molecules A, B and C. All the three molecules are well within the liquid and it is attracted by many forces. Let me now explain to you individually. Now consider the molecule A, which is well within the liquid and it is attracted equally on all sides of the molecule. Therefore, does not experience any resultant force in any direction. This happens only as long as the sphere of influence is well within the liquid. Now let us consider this molecule B. The surface of influence of molecule B lies partly upwards and partly downwards. So the upper half of the sphere contains few molecules attracting the molecule B upwards than the lower half attracting it downwards. Hence, there is a resultant downward force acting on B. Now taking this molecule C, it lies on the surface of the liquid. Half of its sphere of influence lies above the surface of the liquid and half of it lies below the liquid. So here you can see the resultant downward force in this case is maximum only downwards. If a plane RS is drawn parallel to the surface PQ, so if you are drawing one plane over here as PQ and there is another line over here as RS, and then you can see the total downward force is only downwards. Therefore, all the molecules in the liquid will be tending to be trying to pull it downwards only. So if this molecule has Now let us see an experiment to understand surface tension and intersurface phase surface tension by drop weight method. The aim of the experiment is to determine the surface tension of water and interfacial surface tension between water and kerosene in our case by method of drops. There are many methods to find surface tension, but we are using a very simple method called as a method of drops. The apparatus required for this is a glass funnel, a glass tube of suitable diameter, a rubber tube, burette, pinch clip, water and kerosene. The formula to find the surface tension of water is mg by 3.8 into R, where m is the average mass of one drop in 10 power minus 3 kg. G is the acceleration due to gravity in 9.8 meter per second square, and R is the outer radius of the glass tube in 10 power minus 3 meter. And the formula to find the interfacial surface tension is mg by 3.8 into R into 1 minus d2 by d1. Now we have to take the mass when the tube is immersed in kerosene. And d1 is the density of the heavier liquid, that is water, and d2 is the density of the lighter liquid, that is kerosene.
Now let's see the procedure to do the surface tension experiment. A clean and dry glass tube of suitable diameter is fitted to a burette through a rubber tube provided with a pinch clip. Water is poured into the burette and the pinch clip is adjusted so that water drops are formed at the rate of 7 to 9 drops per minute. A small empty beaker is weighed and 20 drops are collected in it. The weight of the beaker is determined again. The difference between the two weights gives the mass of 20 drops. From this, the mass of one drop is obtained. The procedure is repeated for 20 drops again and the mass of one drop is calculated. From these readings, the average mass of one drop is calculated. The external diameter and hence the radius of the glass tube can be determined by using the screw gauge. In the same way, we can find the interfacial surface tension between two liquids, that is water and kerosene. Water, which is the heavier liquid, is taken in the burette, and kerosene, the lighter liquid, is taken in the beaker. The weight of the beaker containing the lighter liquid is filled up half of its volume. The glass tube at the end of which the water drops are formed is kept well immersed in the beaker containing kerosene, so that when the water drop detaches from the glass tube, it sinks to the bottom of the kerosene beaker. Unknown drops of water, say again 20 drops, are collected in the same way, and the weight of the beaker is found again. The difference between the weights give the drops of 20 drops of water formed inside the kerosene. From this, the mass of one drop is obtained. The procedure is repeated again for another 20 drops, which means now the drops in the beaker is 40. And from this, the mass of one drop is calculated as before. From this, for these mass readings, the average mass of one drop is calculated. From the above readings, the surface tension of the liquid and interfacial surface tension can be calculated.
Now let us see the tabulation. So in the tabulation, we have the mass of empty beaker, which is 50.78, and empty beaker plus 20 drops is 51.82, and empty beaker plus 40 drops is 52.76. So mass of one drop for this is 51.82 minus 50.78, which gives 1.04. Similarly, 52.76 minus 50.78 divided by 40 gives 1.98. So mass of one drop is calculated accordingly. So the average mass is 0.05075. So the formula for finding the surface tension is P is equal to mg by 3.8 into R. The value of m is 0.05, g is 9.8, and 3.8 is the constant, and R is the radius of the glass tube which we have taken and found out by using the screw gauge. So on calculating, we get surface tension as 0.06786, around about 0.07 Nm power minus 1. Similar way to find out the interfacial surface tension, we have taken the mass of empty beaker plus kerosene, mass of empty beaker plus kerosene and 20 drops, mass of empty beaker, kerosene and 40 drops. Accordingly, the mass of one drop is calculated and the average mass of one drop is 0.10825. And the formula to find out the interfacial surface tension is mg by 3.8 into R, 1 minus d2 by d1. And mass is now 0.10825 into 9.8, and 3.8 is the constant and the radius is 1.9, and the ratio of d2 by d1 is 0.8, that is for water and kerosene. On substituting these values, we get the interfacial surface tension for water and kerosene as 0.03 Nm per minus 1. By this way, we can find the surface tension as well as interfacial surface tension of any liquid that is given in the laboratory. I hope you have understood surface tension in detail. Thank you.